Good morning. Today I'm going to discuss part 2 of nuclear magnetic resonance, or NMR. We'll spend most of our time looking at proton NMR, although we will later on talk about carbon-13 NMR. NMR gives us 4 main items of information. Okay, first of all, there is what we call the chemical shift. Right, so you'll have a spectrum, and it will show peaks in the range of mostly from about 0 to 10. Okay, we can determine functional groups or chemical environment by the position along the x-axis. Okay, this scale actually goes from right to left. Okay, so for example, alkane CH peaks will show up around 1. If we have protons on a carbon next to a carbonyl, they'll show up around 2 to 2.5. Okay, if we have hydrogens on a carbon next to an oxygen or a halogen, okay, this would show up delta about 3.5 to 4 approximately. Okay, and then vinyl hydrogens, okay, generally about 4 to 6. Okay, sometimes you'll see chemical shifts up to 7 or higher. Okay, and then here's a very common one. If we have aromatic hydrogens on a benzene ring, these will show up at about 7 to 8. Okay, the chemical shift of the particular hydrogens will depend on what other substituents will be on the ring. Okay, aldehyde hydrogens about 9 to 11. Carboxylic acid hydrogens about 10 to 12. Okay, so that's one thing, chemical shift. Okay, the second thing we would look for is integrals, and this is the area under a set of peaks, and this is proportional to the number of protons giving rise to that particular signal. Okay, so if we have something like methyl terbutyl ether, okay, we would expect to see 2 signals. Okay, the methyl signal should be between 3 and 4. Okay, so we'll see a single peak here, somewhere between 3 and 4, since carbon is next to the oxygen. These are farther removed from the oxygen, so let's say this is around 4. And so these will show up about 1. Okay, and if we measure the area under this peak, this should be in a ratio of 9 to 3 or 3 to 1. Okay, sometimes you'll see integrals expressed as the simplest ratio. Right, the third item is what we call spin-spin splitting. If we have n neighboring hydrogens, okay, then we'll see n plus 1 peaks. Okay, I'm going to run through a few examples of that. Okay, let's compare these two isomers. Okay, so this is ethoxybenzene, and this set of hydrogens has two neighbors. Okay, so two neighbors plus one, that would give us a triplet. These two hydrogens have three neighbors, so that would give us a quartet. All right, so our spectrum would look something like this. The CH3, okay, that would show up somewhere between 1 and 2, and it would be a triplet. Okay, by Pascal's triangle, the peak in the middle would be approximately twice as tall as the two outside peaks. Okay, this CH2 is next to an oxygen, so that would show up about 4. Okay, and that would be a quartet. Okay, and these peaks would be in the ratio of about 1 to 3 to 3 to 1. Okay, and then the integrals for both these compounds would be the same. Okay, this would show up as three hydrogens. This would be 2 hydrogens. Okay, this is the number of peaks producing that signal. All right, the second spectrum. Okay, let's look at this. This CH3 would be a singlet, okay, because there's no neighbors. There's no hydrogens on this oxygen. Okay, and this would show up around 4. Okay, so that would be a singlet. And this would also be a singlet. It's feeling the effects both of the oxygen and the benzene ring, so that would be farther downfield. Okay, in this case, maybe around 5. Okay, so we'd see 2 singlets here. Okay, so we could easily distinguish between these two compounds just based on spin-spin splitting. Right, here's an example of where we can distinguish two compounds based on chemical shift. Okay, these would have the same splitting pattern. Okay, this would be a singlet. This would also be a singlet. This would be a quartet, since we have 3 neighbors. This would be a triplet. Okay, so singlet, quartet, triplet, singlet, quartet, triplet. Okay, they would have the same splitting pattern, but we could distinguish between those two based on chemical shift. Okay, so for the first one, Okay, hydrogens on a carbon alpha to a carbonyl would show up between about 2 and 2.5. Okay, so that would be a singlet. And then our CH2, okay, it's on a carbon next to an oxygen. So that would show up around 4. That would be a quartet. And then the triplet would also be, let's say the triplet would be down here somewhere, between about 1 and 2. Okay, for the second compound, the singlet here is on a CH3 next to an oxygen. So that would show up at about 4. The CH2, okay, that would be a quartet. That would show up between about 2 and 2.5, so we have a quartet. And then the triplet would be down here between 1 and 2. Okay, so see the difference? We could, they have the same molecular formula, same functional groups, but we can easily distinguish between those two just based on chemical shift. We'd have a different splitting pattern. Okay, the fourth thing we'll mention just briefly, and that's coupling constant. And we'll come to that shortly. Okay, so I'm going to share my screen. Okay, just to review a few things. Okay, the sample is placed in a magnetic field, and when the right energy of radio frequency radiation is absorbed in order to cause a spin flip, then a signal appears. Different electron densities will shield the nuclei to different extents. Okay, with a more powerful magnet, such as a superconducting magnet, you can get better separation, better resolution. Okay, this is a table of typical values of chemical shifts. Okay, an explanation of why certain functional groups have chemical shifts like they do. Okay, OH and NH signals are highly variable. Oftentimes, OH and NH signals are not split, and they do not cause splits. Okay, and this is because, this last point, there's rapid exchange between the protons and either the sample or the solvent. And so there's a lot of uncertainty as far as magnetic coupling. Okay, some common splitting patterns. Okay, I showed you the triplet quartet that would indicate an ethyl group. A doublet septet is another common one that we might come across. That's an isopropyl group. Okay, let's go ahead and work this one. Propose a structure for a compound of molecular formula C4H10O. All right, the first thing I would do is I would calculate the number of unsaturation units. Okay, and hydrogen has 2n plus 2 times the number of carbons. And so there are 0 unsaturation units, no rings, no double bonds. Okay, so that would rule out a carbonyl or an alkene. So this could only be an alcohol or an ether. All right, so let's take a look and see what we've got. Okay, we've got a doublet. Okay, and sometimes if we, if we're not sure how many lines we have, we just call it a multiplet. Okay, so we got a doublet, a multiplet, and another doublet. And then it looks like we also have a singlet here. Okay. So I would say this is probably an alcohol. And the singlet is probably the OH. Okay, so no elements of unsaturation. There's 4 types of hydrogens, and they're in the ratio of 2 to 1 to 1 to 6. Okay, and this is what I was just saying. The singlet at 2.4 might be a hydroxyl group. All right. So there are only There are only 4 alcohols of this molecular formula. Butanol, and 1-ol, butan 2-ol. There is tert-butyl alcohol, or 2-methyl-propan 2-ol. And then the last one would be isobutyl. Okay, right away, we can rule out T-butyl alcohol. Okay, all 9 hydrogens would be equivalent. And so what we would see, okay, we would see one large singlet for the 3 methyl groups, and then we'd see another peak for the OH somewhere. Okay, that's not at all what our spectrum looks like. Okay, so we have a doublet here between 3 and 4. Okay, that is probably the carbon that's connected to the oxygen. Okay, and that integrates to 2. Okay, so it looks like we have a CH2 there. And this is a doublet, so it has 1 neighbor. Okay, so CH2 next to the OH, okay, that would narrow it down to N-butyl or isobutyl. Right, this is a CH rather than a CH2. Also, this hydrogen would be, whoops, that should be CH2. This hydrogen would be split by these 2 and by these 3. So instead of seeing just two lines between 3 and 4, we'd see about 6. Okay, so that's not what we see. So it doesn't look like it's sec-butyl alcohol or butan 2-ol either. All right, so it's between these 2. Okay, and then This is a doublet. The hydrogens on the C next to the O are a doublet. Okay, so that would indicate one neighbor. Okay, so that means that it's this one. Okay, this says one neighbor. Here, this would be a triplet. Okay, because we have two neighbors. Okay, and then the multiplet, many lines, this is split by these 6 and by these 2. So we would see about 9 lines for that one. And then the methyls have one neighbor, so that's this doublet down here around 1. Okay, so it is isobutyl alcohol. Okay, since we cannot be certain that the delta 2.4 absorption is actually a hydroxyl group, we might consider shaking the sample with deuterium oxide or heavy water. Okay, if the 2.4 ppm absorption represents a hydroxyl group, it will shrink or vanish after shaking with D2O. Okay, if we have an alcohol, okay, D again is a heavy isotope of hydrogen. Okay, what will happen is there'll be an equilibrium. The equilibrium will actually favor the deuterium. So there'll be an exchange that takes place. And the deuterium will not show up on the proton NMR spectrum. Okay. Deuterium does absorb in the NMR, but it's way off scale. So we'll actually see this proton signal disappear. Okay, we can do the same thing with NH bonds. If we're not sure if we have an NH peak, we can shake it with a small amount of D2O and see if the peaks disappear. Okay. In one of my graduate student projects with a student here, we actually did this in order to demonstrate that a particular peak was from an alcohol. Right, coupling constants are the distances between peaks of a multiplet in Hertz. Coupling constants are independent of the strength of the magnetic external field. Multiplets with the same coupling constants may come from adjacent groups of protons that split each other. All right, so one of the main values of coupling constants is with these 3 groups here. You can distinguish between cis and trans and geminal hydrogens using coupling constants. You can also distinguish ortho, meta, and para, and allylic coupling constants as well. Right, so here we have para-nitrotoluene. Right, the methyl down here at about 2.5 is a singlet. There's no hydrogens here. And the A hydrogens here are equivalent. The B hydrogens are equivalent to each other. A is split into 2 by B. B is split into 2 by A, since it's one neighbor. So we'll see a doublet and a doublet. Okay, the coupling constant here is approximately 8 hertz. Okay, that's the distance, the difference between these, the spacing of these peaks. Okay, and since they are coupled to each other, the spacing would be the same. Okay, here is another example of an alkene. Okay, this hydrogen and this hydrogen on the alkene group are not equivalent, so we see two different signals, and each one is split into a doublet by the other. We have two equivalent methyl groups, so that's one large singlet here. And then we have a CH2 and a CH2. Okay, those are both triplets, and that's what we have here. Okay, the coupling constant is approximately 10 hertz. Okay, and so since these are coupled to each other, the spacing is the same. Okay, here we have styrene. And in this case, A, B, and C are not equivalent. And the reason is that A is trans to B and C, and it's cis to C. Okay, so A, okay, which is this proton, this is, it's split by C and also split by B. Okay, so what we'll see is a doublet of doublets. 17 hertz represents the trans coupling constant. And then each one of these is split into two. The coupling between A and C is 11 hertz. Okay, so we'll see this pattern. This is not a quartet because we can see that the spacing is unequal, and also it's not a 1 to 3 to 3 to 1 ratio. Okay, and then this is the chemical shift of, here we have the shift of B. B once again is this one down here. Okay, that's going to be split by A and by C. Okay, so it's split by A, which is trans to it, so that has a coupling constant of 17. And then the geminal coupling constant is about 1.4. So again, we see a doublet of doublets. All right, so we can use coupling constants to assign particular hydrogens to their corresponding signals. Okay, so this this group of signals here between 7 and 8, those are the ones on the benzene ring. And the three alkene signals here, we've got A, B, and C. Okay, here is A, which is this one. It's being split by C and by B. Okay, here is B, and here is C. Okay, if you look at these, we can easily tell that B is a doublet that is more widely spaced than C. Okay, so this would indicate the trans. Okay, it's about 1.5 times the spacing of this compared to the cis. Okay, and then each one of these is a closely spaced doublet. Okay, that's from the geminal coupling. Okay, we can also have splitting because of stereochemical non-equivalence. Okay, so here we have ethanol. And if we were to replace replace one of the hydrogens with some imaginary group Z, these would just be different conformations of the same compound. Okay, with vinylic protons, we can have diastereotopic interactions. Okay, so for this compound, A and B are not equivalent, and the way that we can show that is to replace A by some imaginary group Z, and then to replace B by some imaginary group Z, and these would be diastereomers. Okay, so that shows that A and B are not equivalent, and they will split each other. Okay, here we have another example of diastereotopic protons. A and B are on the same carbon, but they are adjacent to a chiral center. And so replacing A or replacing B would give us two diastereomers. And so these will split each other. Okay, and here is the NMR spectrum of 1,2-dichloropropane. Okay, the methyl group, okay, has just one neighbor, so it's split into a doublet. Right, this hydrogen is split by, okay, it's split by the methyl, and it's also split individually by each one of these, so we get a multiplet. And these two are not equivalent. Okay, they're split by this one on the neighboring carbon. They're also split by the one on the same carbon. So we get a more complex splitting that takes place. Right, the NMR experiment has a slow time scale. So molecules are tumbling relative to the magnetic field. So the NMR just gives an average spectrum of all the orientations. Okay, for example, axial and equatorial protons on cyclohexane interconvert so rapidly that they give a single signal. Proton transfers for OH and NH may occur so quickly that the proton is not split by adjacent protons in the molecule. Okay, so here is ultra pure ethanol. And in this case, we do see splitting. Okay, so there's no solvent to exchange with. This is very high purity. And so we do see splitting from the H and on the H. Okay, but if we have a solvent, if we have any impurities, then the hydroxyl proton will just show up as a singlet, and the CH2, CH3 will show up as a triplet quartet. Okay, and this is almost always what we're going to see with something like ethanol. Okay, we very rarely would see splitting on the H or by the H. Right, a lot of times NH signals will show up as broad peaks. Okay, and this is because of a moderate rate of exchange. These are exchanging with the solvent. In the case of ethanol, okay, we had a rapid exchange taking place, so we see a narrow peak. And because of the moderate rate of exchange, there's some uncertainty about what the spectrometer sees. Okay, so these may be broad. Okay, and this is what I mentioned earlier. One way we can verify that we have an NH or OH peak is to shake the sample with a small amount of heavy water, deuterium oxide. And if that's the case, the signal will disappear. You might also mention that since deuterium doesn't show up in the proton NMR, okay, we usually use deuterated solvents. One that is very commonly used is what we call chloroform D. The hydrogen has been replaced by the deuterium. Okay, if we used ordinary chloroform, okay, this has a hydrogen, and that would absorb, and usually there's quite a bit more solvent than there is sample, and so we'd get a huge peak from that hydrogen, and that would just swamp out everything else. Okay, we typically do see a tiny peak. There'll be a small amount of solvent which is not deuterated, so that'll show up in the case of chloroform D. Ordinary chloroform shows up at about 7.2. Okay, and then some other solvents include acetone D6, okay, where all of the hydrogens are replaced by deuterium, DMSO D6, benzene D6, and then you can also get deuterated acetonitrile and methanol, for example. Okay, now we're going to turn our attention to carbon-13 NMR. Carbon-12, which is the most abundant isotope of carbon, actually has no magnetic spin. It has an even atomic number and an even mass number, so the spins of the protons and neutrons cancel each other out. Carbon-13, though, does have a magnetic spin, but unlike protons, protons represent the most abundant isotope of hydrogen, whereas carbon-13 is only about 1% of carbon that occurs in nature. Okay, another difficulty is the gyromagnetic ratio. Okay, that's a proportionality constant between the magnetic field and the energy, is only about 1/4 that of the proton. And so for this reason, many years ago, a technique called Fourier transform spectroscopy is used. And in fact, Fourier transform spectroscopy is also used in proton NMR. But this is important because we can take many, many scans, even thousands of scans, and average them to get a better signal to noise ratio. Okay, so in Fourier transform NMR, okay, this is what all NMR instruments today use. Okay, we have a radio frequency pulse, which is delivered. Nuclei absorb energy and precess or spin like little tops. Complex signal is produced and then decays as the nuclei lose energy. And then this produces a signal called a free induction decay. And then the Fourier transform is a mathematical operation which converts this to the signal. Okay, for carbon-13, we have a whole different set of chemical shifts. And this is a very abbreviated listing of some of the functional groups. Okay, so alkane carbons will show up between about 0 to 40. Halides will be somewhere in this region. Alcohols and ethers will show up somewhere about 60 to 90. So will alkynes. Alkenes and aromatics will show up usually about 110 to 150. Carbonyls, okay, about 160 to 210. And within that, okay, we can distinguish among the different types of carbonyl compounds based on where they are in this range. Okay, so esters will typically be at the lower end, whereas aldehydes and ketones will be at the higher end. Okay, so here is a compound in which we have both the proton and the carbon NMR spectrum. Okay, this was done in chloroform D. Okay, here's this little tiny peak here, which represents a little bit of undeuteurated chloroform. Okay, and we have 4 singlets. Okay, the aldehyde proton is showing up here at around 9.4, okay, which is what we would expect. That's a singlet since there's no neighbors. Okay, and then the other 3 here. Okay, are shown here, and apparently the NH is not showing up here. Maybe it's just so broad that we don't see it, or it could be superimposed on this one here. Okay, and then once again, 0, that is the reference, the TMS that's been added. Okay, and then above it, we have the carbon-13 NMR. Okay, since deuterochloroform contains a carbon, okay, it will show up in the carbon-13. It'll show up about 77, and we'll see 3 peaks of about the same height. Okay, so that's just the solvent peak. Okay, so the number of carbons, we have 1, 2, 3, 4, 5. Okay, so we're seeing 1, 2, 3, 4, 5 carbon peaks. Right, the aldehyde carbon, this is the one that's most downfield, about 180. And then the other 4 carbons here are represented by these peaks. Okay, the smallest one here, okay, we can predict that's the one that doesn't have any hydrogens on it. So that would be this one right here. Okay, and then as far as assigning the others, okay, that's a little more difficult, but this would be the one that has no hydrogen on it. Okay, notice here that the splitting on the carbon peaks has been suppressed, so these all appear as singlets. Right, the resonance frequency is about 1/4 that of hydrogen. And so we would want to use a stronger magnet. Peak areas typically are not proportional to the number of carbons, although with a little work and some advanced techniques, we can achieve that, but generally this is not the case. Carbon atoms with more hydrogens absorb more strongly. Okay, it is unlikely that a carbon-13 would be adjacent to another carbon-13. Okay, there's a very low probability, so splitting by carbon is negligible. It is possible to run an experiment where we do observe carbon-13 to carbon-13 splitting. You typically have to run the experiment for several days in order to achieve that. So it's something like the probability is something like 1 in 10,000 that you'd have two carbon-13s next to each other. Carbon-13 will magnetically couple with attached protons and adjacent protons. Okay, and so because of that, this will produce some complex splitting patterns which may be difficult to interpret. Okay, and so one way to simplify that is to use some decoupling techniques. Okay, so to simplify the spectrum, protons are continuously irradiated with broadband noise, so they are rapidly flipping. The carbon nuclei see an average of all the possible spin states. Thus, each different kind of carbon gives a single unsplit peak because the carbon-hydrogen splitting was eliminated. Okay, and that's what we saw in the spectrum that we just looked at. Okay, so here is 1,2,2-trichloropropane. Okay, below we have the proton spectrum. All right, this CH3 is a singlet since there's no neighbors. CH2 is also a singlet, there's no neighbors. And we have 3 carbons, so 3 different signals. The one with no hydrogens, okay, that is the smallest peak here. And it's also most downfield because there's 2 chlorines attached. Okay, we also use TMS as a reference for carbon-13. Okay, another type of decoupling is what's called off-resonance decoupling. And in the previous slide, all the carbon peaks showed up as singlets. Okay, here we decouple the proton-proton interactions on adjacent carbons, and we suppress everything except the proton interactions that are directly attached to the carbon-13. And again, we apply the N+1 rule. Okay, so a carbon with no protons attached, okay, N+1, that would be 1. 0 + 1 is 1. Okay, so this one appears as a singlet. A carbon with 3 hydrogens attached would appear as a quartet, and a carbon with 2 attached would appear as a triplet. Okay, and then TMS, of course, is a quartet. Okay, so to interpret carbon-13, we can look at the number of different signals to indicate the number of different kinds of carbon. And since the spectral window is so large, from about 0 to 200, it's rare that carbon signals overlap, but they do sometimes. The location or chemical shift indicates the type of functional group, okay, just like with proton NMR. The splitting pattern of an off-resonance decoupled spectrum indicates the number of protons that are directly attached to the carbon. Okay, so here is butan-2-one, it's a ketone. Okay, the carbonyl carbon is way downfield, around 210, and it's a singlet. There's no hydrogens attached. Okay, if we do the broadband decoupled, okay, all the carbons appear as singlets. Okay, we've got 4 carbons of 4 signals. And if we do the off resonance decoupling, we can see the splitting. Okay, so the 2 methyl groups will appear as quartets, and the CH2 would appear as a triplet. Okay, and the quartet that is most downfield or to the left, okay, that's likely to be the one that's next to the carbonyl. There's several spectral editing techniques for carbon-13 NMR. Okay, one of them is called DEPT, and it's easier to run with Fourier transform spectrometers. Of course, today virtually all NMR instruments are Fourier transform. Each carbon-13 nucleus is magnetically coupled to the protons bonded to it. Okay. Okay, so this is a way of another way of detecting how many protons are bonded to a particular carbon. Okay, so here's the cyclic ester, and the carbonyl carbon is showing up here at about 175. Okay, it's a singlet. Okay, no attached protons. And all of these other carbons are CH2s. Okay, so they would all show up as triplets. If we do the broadband decoupling, okay, we have 1, 2, 3, 4, 5 carbons, and that's what we have in the compound. And okay, all of these are triplets, and we've got 2 triplets that are overlapping. Okay, next I'm going to briefly discuss magnetic resonance imaging, or MRI. Okay, this is a non-invasive diagnostic tool. This came out in the 1980s as an experimental diagnostic tool, and up until the 1990s, it was considered experimental, and it wasn't covered by insurance. Now today, it is recognized as a valid diagnostic method. In the early days, they originally called it nuclear magnetic resonance imaging, and this was about the time of the nuclear disasters at Chernobyl and 3 Mile Island. And so the term nuclear was very scary to people, and so they omitted that term and simply called it magnetic resonance imaging. Okay, so a computer puts together 2-dimensional slices to get 3D images. This has a number of applications. It can be used to detect tumors. Okay, here is one example. We've got a metastatic tumor in one hemisphere of the brain. Okay, here is a MRI of a pelvic region. MRI has also been used to get the exact dimensions of a knee joint, for example, so that they get the correctly sized prosthesis when doing a knee replacement. Okay, so that is the end of this particular lesson.